And we shall start very shortly. All right, so let's see. It is 20 to 12. I'll try to make it within 1 hour 15 minutes. Of course, it won't work, but you know, that's the part of the game. So today I want to speak to you about this TDA, which is an abbreviation from topological data analysis. I will be doing hopefully some exercises in Python. So if you happen to have a Jupyter notebook installed on your machines, it shall be fine. Otherwise, we'll help you to set it up on Google Colab or whatever you like. So that's roughly the plan for today. We have a number of exercises, but let's try to cover some theory first, right? So the schedule is we'll start with persistent homology, move to conventional and the ball mapper. Again, given the time we had, if you want to do some exercises, there's absolutely no way we can do the theory right. So we'll stay on the intuitive level, and we'll try to have a few practical results. All right. If there are any questions, please feel free to ask them straight away. That's the plan. So let's start with the credo, which I think is attributed to Dlotko, one of the founders of the discipline. You know, about the shape of the data, that it has meaning, that it brings value. And indeed, it can bring value if you actually start a company out of it. I think that's a good idea. It's a good plan for scientific life. However, that thing is quite, I mean, it shouldn't be a surprise if you ever done an linear regression. So then let's think about it conceptually for you. So you have a collection of points like the points over here. Now what we can do is we can build a model of this collection of points. But by solving least square minimization problems, which will give us two numbers, A and B, constitute this line. So this line is equal, can be parameterized by y plus ax plus b. And that line gives a good model of the data in the sense that for a given x, I have a pretty good idea what the y value will be. And so if that trend corresponds to something I don't need to store all the data, I actually may have a certain model of the data. And the point that I can fit in the line, the simple manifestation of something deeper that this point not happen to have an inertia. Okay? Problem is, most of the phenomena in nature don't like to be there. I'm not sure if this is better good with the fact of life. So as you start to work with point clouds, even in 2 dimensions, you will see the whole zoo of possible shapes. Some of them may be circular. I mean, if you ever work with some sort of periodic, semi-periodic behaviors, quite likely something will be moving around. Cycles, if you start to play with some chaotic attractors, you may get, butterfly attractors, so something moving around. Figure 8, not necessarily one way or the other. There are all the Y, X letter shapes, and we see this type of point clouds. And quite often the interpretation is that the center is the normal state, and those flares are subabnormalities. And then we'll see a few examples like this later on. And then the problem is, we have a bunch of different behaviors. So in principle, we can just sit down and try to fit, another equation, x squared plus y squared equals r squared equals some positive constant, to fit it over here. And then we can figure out an equation for the figure 8. Perhaps we can figure out, the equations for x and y. The problem is, first of all, we quite often a priori don't know what is the shape of R. Over here, those data are 2-dimensional, so we can visualize them. Cool. We'll get back to this idea. Oftentimes, there are 500, 1000 dimensions. What to do with that? I mean, we can blindly try to fit the model look at the R square or something like this, but that, always will do some overfitting, and at the end of the day, data have very different shapes. And it's very hard to try to guess what is the shape there are and try to fit the right model. That's why we are not going to do this. We are going to do something else. And so let's see what's the next slide. The next slide is here. And of course, when I'm speaking about the data, collection of points, typically in array. In general, it can be any metric space, discrete metric space. Let's think for the moment about n-dimensional Indian space. There is an obvious thing we can do. Okay, and there are different shapes. How about we compute the summary statistics of those collections of points? I think Shaya will be speaking also about the shape of the data, right? So I have two examples. Unscombes quadrat. So there's a collection of points. If you compute the basic summary statistics, average over x, average over y-axis, standard deviation over the axis, the correlation between those two axes, those two numbers for every so standard deviations and averages for every of those point clouds, and the correlation between every pair, that they will be very similar. However, as you see, the shape of those point clouds is vastly different. This is a quite classical example, I think, from the 70s. Later on, they had this Datasaurus dataset, and you see exactly the same phenomena happen. So if you look at the mean standard deviation over the axis or the correlation between them, up to the third significant digits, they are all the same. So if we just, route our point clouds to an Excel file and then compute the summary statistics, we'll see, okay, each of those point clouds is similar to every other. However, when we visualize them, of course, we see that they are vastly different. And again, the main message, both from Unscombes and from Datasaurus, is that, well, of course, you should be using statistics, but you should also visualize your data. And that's a very good message. Your data are two-dimensional. Question is, what can you do with your data if you're looking for G expression data, which oftentimes are 500-dimensional plus? Well, visualization in this case is problematic. And that's what I'm going to cover. All right? Yes, so again, visualization is important. You can compute various summary statistics for data sets, but then we should try to visualize them. And question how to do it. And again, already in the first slide, we have those keywords like persistent homology, like Dlotko. There are some gadgets which, in some cases, may allow to tell us, okay, those look similar, those are different. That's what we will be practicing. Okay, so the whole pipeline we'll be looking at, we'll be starting from point clouds. Although if we have time, we can actually look at some image data, we can look at physical complexes. We'll see how quickly it will work. We'll compute some topological descriptors. We'll be speaking about data numbers, the Euler characteristics, maybe persistent homology, and the mapper. And then we can do some inference, either by computing a distance between those descriptors or by simply looking at this. Is the visual aspect. Okay, so let's start to build our topological descriptors. There are essentially two phases in the building process. Typically, we are starting with some combinatorial representation of our data, and then we will be doing some algebra on the top of this combinatorial representation. Okay, so let's start with combinatorics, and the main workhorse, not the only, but the main, statistically the most typically used, is a simplicial complex. And again, we can define it geometrically, but we won't have too much time to do it. So let me jump immediately to that concept, which is called an abstract simplicial complex. And that's a simple data structure. So K, script K, is an abstract simplicial complex. Even only if, I'll tell it twice, so that everybody's clear on that. For every element from this collection, if I take any subset of that element, this subset has to be in this collection. So I have a collection of objects. I take one element, that's a set, and taking any subset of this set, it has to be an element of this set. Okay, so let's think about it. Let's take a two-dimensional simplex. So we have three vertices which are linearly independent, and we are taking a convex side of those vertices. That's a geometrical two-dimensional simplicial complex. What's the corresponding abstract simplicial complex? Well, it will be collection of three elements. If I call my vertices ABC, it will be a collection, a set ABC. What this condition means that every subset has to be an element of the collection. Well, it means if I take a set ABC, I take any subset, say A, is this vertex? Well, this vertex has to be in my complex. What does it mean? Maybe let's take one more. If I take a collection ABC, I take a subset containing of an element A and B, it also has to be in this collection. What does it mean? Well, it means that if I have a complex that happens to have a triangle ABC in it, you need to have every boundary element of this triangle, right? So it really means that the boundary of every simplex is in my simplicial complex. As simple as that, right? Make sense? Okay. Again, every simplicial complex has a geometrical realization. As written in embedding theorem, that there are different questions to which dimension I can embed that particular simplicial complex. Always I can embed it to dimension of complex times 2 plus 1. In some cases, I can embed it to lower dimensions. That's a totally separated field of study. We'll not get there. But you can move between the abstract representation and geometrical representation for the purpose of playing with those ideas. On a computer, of course, abstract representation is easier because it's a combinatorial data structure that is quite easy to count. So we'll mostly stick with that, right? And again, simplicial complexes are not, of course, only used by topological data analysis or by topology. You are doing finite element methods and meshing certain objects and then solving some equations to get some mechanical properties, electrical properties, etc., etc. And you are working typically on this type of meshes. And that's very, very much related, and also applied topology applies to this type of mechanical problem. But that's another story. If you want to know more, ask me later. Okay. Okay, so there is the first quiz question. If I show you this collection of points, what do you see? Again, we are speaking about visualizing our data set. I told you, okay, it's easy when it's two-dimensional. So I'm giving you a two-dimensional data set. What do you see? Cycle. Yes. It's not one of these crazy experiments, with psychology and maths and whatever. No, not this time. Let's cycle. Any other guesses? Of course, that's an extremely vague question, right? So you can say pretty much anything. But if there is one of these games, a cycle for one at the top, somebody can say 19 points if you count quickly. I think there are 19 points over there. Then you can try to merge those two guesses and say, okay, maybe those are 19 points sampled from a cycle. And question is, can we try to make this observation a bit more formal? Can we make it more precise? And what I will try to do is I will try, starting from this collection of points, to define a simplicial complex. That simplicial complex will not be static. Somehow, in the different scales, it will look differently. And the observation that we see a cycle at some point will manifest itself in a simple fact that the homology group of the complex for quite a big range of parameters will be the same as homology of the simple. Okay? That's how we do it. So what I do is I put a ball of radius r centered at every point of this point cloud, and I let r grow from 0 to infinity. And then I'm taking the union of those of those balls. So if the radius is 0, we just start from the point out, as you see it over here, for a bit. And of course, this is just 90 points. For a bit larger radii, we'll have this shape. And if we contract it continuously, we get something that we can continuously deform into a circle. If I increase my radius a little bit more, well, there is still a hole over there. I can still continuously deform it into a circle. And only for quite a big radii, it's not possible anymore. I can keep increasing the radii and everything that we kind of have a single connected component and no holes. Okay. But what's important is that for large range of radii, we'll see something that can be deformed. Okay. Okay. How to make it precise? How to define this object that I was speaking about? And how to implement it? So, what do we need? Again, that's kind of a semi-computer science description. So we need an input, a procedure to construct the thing. We need to tell what the output is. So the input is a collection of points. Let's say I have a terrible this n and that n is not the same. So I have k points, p1 to pk. That's a finite collection of points with a metric d. You can think about points in Rn, standard Euclidean metric. You may think about discrete metric space. Doesn't matter. We are defining this thing, which is a Rips or the torus Rips complex. What it needs is this parameter epsilon. Remember, I was speaking about the radii. Now I call it my radii epsilon. Actually, my radii is epsilon over 2. So what's the definition? So Rips complex at the level epsilon consists of simplices supported in the points p0 to pn. Again, this n and that n, they're not the same. Excuse me for this collision. Even only if the distance between every pair of points from p0 to pn is bounded by epsilon. It's less or equal than epsilon. So if I have a subcollection of points, so that the diameter of this collection, the maximal distance between a pair of points from this collection, is less or equal than epsilon, then I put a simplex in this collection. Do you remember the definition of an abstract simplicial complex? How do you remember the definition of an abstract simplicial complex? It has to be closed under what? Subsets. Absolutely. So let's see, if I take a subset of that collection, the diameter of the collection is less or equal than epsilon. The diameter of the subset is also less or equal than epsilon. That shows that the torus Rips complex is indeed an abstract simplicial complex. That's fine. But we can also attribute to every simplex, the first epsilon from which we see it will be exactly the diameter of that simplex or the maximal distance between vertices. And I will call this value a filtration value of a simplex. Okay? So let's actually see a simple example where my point cloud consists of 4 vertices. And for epsilon 0, my balls have radius epsilon over 2. I see 4 vertices. Topologically speaking, I see 4 connected components. Okay, let me increase the radius a little bit. Then, the first non-trivial event will happen. Let's see. So those 2 points are the closest one. Oops. So the moment my epsilon reaches the half of the length of that edge, or my epsilon reaches the length of that edge, the radius of my balls reach half of the length of that edge, I will see this edge being formed. Right? In this case, for that level of epsilon, let's forget about it. So let's speak about distances between points. So if the distance, my epsilon is equal to the distance between those 2 points, I will still see 4 vertices, but 2 of them will be connected by an edge. Okay? How many connected components do you see over here? 3 connected components. Good. And then, yeah, that is also pretty unfortunate. pictures, so it's not clear which one is the next. But let's see. Let's assume that the distances between this point and that point, and this point and that point are comparable. Then those two edges will appear at the same time. We will have additional two edges. But there is not the only thing that will happen. So if we have those three edges, we also have a triangle, two-dimensional simplex, because again the diameter of for the radius, which is equal to the length of either this or that edge. Also, this triple of points start to constitute a simplex, so a triangle. Okay, how many connecting components do we have? Two. And let's see, the next one. Let's see that this point is a bit closer than the other one. So if we increase this epsilon by a little bit, we'll see this edge appearing. Right now we only have one connected component. And with the next edge, we'll have this triangle being formed. And there is essentially one more change that can be made. So if we increase our epsilon considerably, we'll have that edge being added. And in the same time, all the points will form a simplex. So we'll have one tetrahedron or one three-dimensional simplex. All right. So when we have a collection of points and we compute the distance matrix between them, we can run this construction more or less effectively, but that's what we can compute. And that's, if we start from a discrete collection of points, this is how we can get a combinatorial representation of the data. Very much like, in this example, when we started from point sampled from a circle, with a certain level of epsilon, with a certain level of radii, we start to see really something that can be continuously from the circle. Okay, so that's an advantage. There is a disadvantage. Those complexes can go large. And what do I mean by that? Well, you start playing with it, and we'll start playing with this very soon. Quite likely you may run out of memory, you may need to restart your machine. So let me warn you right now, and I will warn you again before we start. If you have any unsafe work, save it, close it, and then all right. But why? So the problem is, if I have a collection of points, I'm not sure how many times, something between 10 and 20 points. If I choose my epsilon being close to the diameter of this point cloud, then I will have, of course, 10 vertices in this collection of points, the cardinality of the collection of points. But I will have n choose 2 edges. Okay, that's not too bad. But then I will have n choose 3 triangles, n choose 4 tetrahedras, n choose 5, etc., etc. So if you remember, if you actually sum up the binomial coefficients, that actually sum up to n factorial, which is going exponentially, that will kill your computer, and that will essentially kill any computer you may have. Okay? So there are two things we are doing in practice to prevent that from happening. First of all, we never choose such a large range, right? Never ever. And there are different types of complexes you can choose to prevent it. Again, we don't have time to talk about this today. If you want, I'm more than happy to talk over lunch about alpha complexes and another types of complexes that are more efficient. That's one thing. So we never choose a radii that big in theory. In practice, we always try. That's why sometimes we need to rest some questions. But we also never generate all the simplices. So we always say, okay, I'm only interested in the simplices up to dimension 4 or 5. Typically, this is 3 or 4, maybe 2. Okay. So even if we get this combinatorial explosion, we have n choose 1, n choose 2, n choose 3, and then stop. Still quite likely your machine may be killed, but that's a risk you need to take. All right. So I warned you. That's what it is. Okay. So let's see how we can proceed further. So we have a simplicial complex. In theory, we know how to construct it. We'll construct it in practice in a second. And then here comes 101 lecture in algebraic topology. Usually takes a semester. So you define, the concepts of chain, cycles, boundaries. those are our groups, and there's a subgroup operation. So some boundaries is a subgroup of cycles. Cycles are a subgroup of chains. If you take a group of cycles, quotiented by the group of boundaries, you get something which is called the homology. Then I won't even try to define it formally. More than happy to show you the appropriate resources. All I want to tell you is what is the idea of homology. So homology, it's an object constructed to count holes nowadays. Okay, you can see what's over there, how many holes we have.
What in which dimension?
That's exactly the answer. In dimension 2? 0. So what's a hole in dimension 2, right? So if you take a ball, right? So typical, I think if you take a football, it's pentagons, and there's one with 6 sides. If you take a volleyball, it's different thing. But everything boils down to the fact that the hole is whatever is inside, and it keeps the air inside and kind of pressure to move away to the external environment. So a hole in dimension 2 is what's inside the ball. You can think about hole of dimension 3 as something bounded by a 3-dimensional sphere or a 3-dimensional torus. There are different options, and you need to have a collection of, let's say, in case of a hole of dimension 2, it need to be a collection of 2-dimensional simplices that has the property that they are cycles, so together they have empty boundary, so they surround something, but they're not a boundary themselves, so they have to surround something in the middle. Okay, I tried. Hole of dimension 1, we can actually visualize it over here. So there's a hole over here. And we can represent this hole, for instance, by these 3 edges. So if I take a collection of these 3 edges, this is a cycle. What does it mean? Well, if I compute the boundary of the cycle, well, this vertex will be in the boundary of the cycle, this vertex will be in the boundary of the cycle, this vertex will be, and as well as this vertex will be in the boundary. But because of each of the vertices is present in the boundary twice, they cancel out algebraically, and the boundary will be 0. So that thing is a cycle. Let me show you another cycle. If I take this edge, that edge, this edge, this edge, it's also a cycle for exactly the same reason. Every vertex, maybe this, and that, is present in the boundary of every edge twice, of every edge from the cycle twice. So this cycle, this collection of 4 edges is a cycle. This collection of 4 edges is a cycle. But there is something different between those 2 cycles, right? Can you tell me what it is? Okay, plain English, please.
Sorry?
One is filled in, right?
Yeah.
And the other one is not. So look, if you think about this cycle, if I take this triangle and that triangle, and compute the common boundary of this triangle plus that triangle, this edge will cancel out very much because of the same reason as if I have 2 edges meeting in a point. This point will cancel out in the sum. So this edge will cancel out, and what will remain in the boundary will be the external side. So that's a cycle we can generate from a higher dimensional simplices, and therefore we call it a boundary. This cycle, at the other hand, is not a boundary. And let's just think about it. So if it was a boundary, probably I would have to add, this triangle, that triangle, this triangle, that triangle. But then I need to add, all the other triangles. So a possible candidate for something that has this cycle in the boundary will be the collection of all triangles over here. And then if you compute the boundary of this collection, it will contain this cycle, yes, but also that cycle over here. Therefore, not the cycle alone. And in fact, this cycle is not a boundary, so we cannot find any collection of two-dimensional simplices having this cycle and only this cycle as a common boundary. And therefore, that cycle is not a boundary. So remember when I told you about homology, quotients of cycles divided by boundaries. So we want to find cycles that are not boundaries. That cycle will represent a non-trivial element in homology. That cycle over here will represent a trivial element. Moreover, this cycle over here, that cycle over here will represent the same element in homology. Why? Well, because they are different by a boundary. This cycle and that cycle, they are different by the boundary, namely all the triangles we have. Intuitively, does it make sense? It's allowed to say no. Yes. Good to acknowledge that you agree with that this is allowed to say no. Okay. How many connected components? One. So we can move from every point to the other point. Within our data set, okay, I won't go into this. So those are homologies. Homology are telling us what is the number of connected components, what is the number of poles in dimension 1, what is the number of poles in dimension 2, etc., etc. But now we have this Dlotko Rips code. It's a competition parameterized by radius. And that's the question, okay, if I increase my radius, new simplices appears. How the homology groups are changing, how they are evolving. Remember the cycle examples. We started with 19 points, and for some small value of radius, we saw a cycle that was present or persists for a large collection of radii, and eventually disappear when the middle of the cycle was good in. How can we track the evolution of homology? Well, that's something that persistent homology is doing. Track the homology for the constitutive radii. And that's a very, very nice thing, because you get somewhat multi-scale information that is robust. We'll play with that. You have a metric structure. We'll play with metric in the persistent diagrams. It can be applied to a variety of complexes. We'll mostly be working on the Dlotko Rips complexes. By all means, that's not what we can. That's not all what we can do. Can be applied to time series analysis, similarity measures, etc. Okay. Okay, what's this? Okay, I should move it. Spoiler alert. Okay, you know the torus. Who knows what it is? No. Yeah, who knows? Okay, so that's a torus. So yeah, you know what it is. Why your hand was shame. Okay, so that's like anybody played Snake in your lifetime? The thing that used to play on the Nokia frequently. Yeah. Snake is the game. You are moving with the snake and into it pixels. What happens if I'm a snake and I move to this wall? What happens? I reappear over here, right? And if I move to this wall, I reappear right here, right? That's exactly what the torus is. So look, we have certain vertices, and if you look at the boundary, you have 0, 3, 4, 0, and exactly the same thing over here. So if I move over here, I reappear over there, because those two things are exactly the same. Likewise, if I move over here, I reappear from that side. So that is a torus. And that's a triangulation of it. So you have a sheet of paper, and of course I don't. What happens if I take a sheet of paper? If this side is the same as that side, then I can just roll it, and what I will get is a cylinder. Right, so this is this intermediate step, but also, you know, that part of the cylinder and this part of the cylinder is the same, so I can just roll it, and I'll get a torus, right? So that's why this flat torus which we have over here is exactly what you normally think about torus. So a tire, people say donut, but you know, donuts are typically not empty inside. So mathematical torus is empty inside. If you're speaking to engineers, torus are fed in because they want the torus to guide electricity. Mathematics there, you know, different conventions. Anybody wants to play with a torus? Who wants to play with a torus? Who don't want to play with a torus? Let's see. If I'm asking a network one question and the negation, and I'm not getting an answer, what does it mean?
You want to play with it.
Who wants to? You want to play with it? Good, thank you. So let's see. We'll try to do it on Jupyter notebooks. If it doesn't work, but then Jan, can you help with the co-op? So the idea is we go to Dioscuri TDA.org. We go to, I think, conferences, and yeah, sorry, we are going to this tutorial down here. And you download that thing. Sorry, I'm recycling examples. There are many more examples you can play if we have time, but that's next to impossible. And then what you try to do, and here comes the tricky part, you are running a Jupyter notebook. So first of all, download that thing. When most of you download that thing, I'll move to the next one, right? Okay.
Yeah, so the link is different.
The link is different?
Yeah.
Okay. Just go to TDA to Google.
You have to click on here's the tutorial and not on the second part. So you just go one step back. Click on here's the tutorial and not on the second link. I gave on a scroll. That is the one. First one. Then you get it.
Well, you know, it brings you somewhere, but not to the right place.
And then go on conference. There. Not on the second. Yeah, exactly. Yeah, there are two links and that you not really know. What was the second one? This is going. Yeah.
Once you download, try to open Jupyter Notebook, please. The School TDA conferences, bottom left link. Okay.
Well, there's some technical numbers.
Yeah, it's for advanced people. No, it's right, but you need to scroll down. And then this exercise is consistent homology.
Yes, so before you start, you may need to do Exclamation mark, pib install goodie. It's running, it's running. So let me actually write it down. So first of all, Google Dioscuri TDA conferences. Bottom left link. Download, and then you do exclamation mark. And then you should have everything that is required.
Okay. Bottom left.
Bottom left. No. Conferences. Is it?
Yes. I'll try it. No, it didn't work. It's better than everything.
You have your Google.
Google what?
So are you logged in on Google? Because you need an account to access Google Colab.
Yeah, sure. I mean,
And do you have this on your local machine?
yeah, that's on my local machine.
Okay. So
Yeah, I think post contact I should also put on last. Can you do? Good. What do you need?
oh no.
New one.
No, we didn't import it, but I want.
Okay, guys. So jest już tutaj common one, nie? Możesz otworzyć Jupytera?
Oh, I can. No. Can I plug my laptop in to the?
Yeah, but we will not be streaming. Okay. So what's the problem?
No, can you just set it in English so everyone can see what? No, I need to set the Google thing to English. No, you have to go to your.
Yeah, I know. Wait a second. Dobra, otwórz coś nowego. New.
Dobra, to sobie.
Dobra, zrób sobie trochę. Okay, send. Choose file.
Okay, which one?
Okay, so another thing you can do, you can go on Google Colab and you can send the whole thing, and then it will open in Google Colab. And what I need to do is to do install goodie. It will take a moment. Yeah, you're right.
Oh, yeah, that's it.
Ah, so on Google it's quite quick because the downloads are much better. We have good installed, and then we can click through the others. So you can also do it in the in color.
Windows machine. Yeah, you can just. Somehow people use the right. Oh, okay. For me, it was like
Have you ever encountered a problem like this?
Oh, yes. Okay. Which version? It should be quite okay.
You can check the version. Will you do version with open and close?
No, then just one.
Working? Yeah, that's good. Oh, yeah, you were supposed to start with intro homology. Let me go back. Yeah,
Yeah.
try again. Yeah, reload it, have it. Yeah, so I will show you.
And then add it to comment again. Yeah, and then save it. Okay. Open that and then wow, it's corrupt. So they don't need to edit. Sorry, a moment. Yeah. No, but it is working, but it is not finding the right final. Yeah, I'm just so now adding them one by one.
to 5 J to 5
Yeah. So for everybody, if it's still not working or if you need to sign out of Google, I made a tiny URL for the first file and I'm adding the others, where you can just open it and run it and it will come up and it works. So adding the other two, so this is the intro to homology. I'm adding the other ones and writing them down so you can don't have to do it manually. I will do it.
So I didn't try to run the. So I have yeah, okay. And the second one.
Yeah, I'm just thinking about the work.
Yeah, yeah, I use a different propaganda different thing. That's like I want to screw it in the thing.
Change something.
You get the right thing.
Yeah, but can you change it and run it without saving? You're playing with it. I was trying to there.
You need to change a triangulation to get some other thing. But I'm not sure I'll give you enough time to complete it right now. So, okay, everybody is more or less on the right stage. So let me check the time. Okay, we are 1 hour into our exercise, our lecture. So my suggestion is, if you are able to compute homology of a torus, that's already half of success. If you want to speak today, later today, or tomorrow, we can play with other two-dimensional manifolds. You can think about triangulation of a sphere. Think what's the simplest triangulation of the sphere? How many two-dimensional simplices you need to get something which can be continuously deployed to the sphere? How many simplices? Can you tell me? 4. You know that. Can anybody else say 4, please? 4. Thank you. And then we can, do a real projective plane. We can do a Mobius strap. We know other homologies of those objects. We can try to see if the code is working well by computing the homologies. Once you do real projective plane, you will notice that we are using coefficients from Z level, ZP, for triangle. Because you are not seeing something like a torsion coefficient, we can also do the torsion coefficients. That's another story if you know what I'm speaking about. If you don't worry, that's a bit more involving. Anyhow, so that was the first exercise. Where's my point? That was the first exercise. Let's carry on. So what we did, there was no filtration. We just told the computer, here are the list of my triangles, right? And we took the triangles roughly from there. So we had, let's see, this is 9 times 2, 18 triangles. And it actually generated all the vertices and edges. And it created what we wanted, which was a triangulation of a torus. There was no radius involved, so we didn't have a point cloud. So that was homology. That's, end of the 19th century, beginning of the 20th century, Henry Poincaré idea. Let's play with the parameterized version of homology. So this time we don't have a point cloud as an input. We want to construct the Dlotko's Rips complex of that point cloud and compute homology of this Dlotko's Rips. And what we'll get will not only the homology groups, but it will be a collection of points in the plane. Every point in the plane has 2 coordinates. Normally we call it x and y coordinate. In TDA we call it birth x and y, which is that coordinate. The birth coordinate tells us the radius, that the epsilon level for which we for the first time we see a given homology class. The depth time, as you may guess, tells us what is the radius epsilon for which we see this homology class for the last time. What does it mean for the last time? Well, either it became trivial or it became either because of some other homology class that was created. So what we will do in this persistence underscore simple underscore point underscore cloud is, excuse me. What we will do over there is we'll sample points from a circle. We will compute homology, persistent homology. What do you expect persistent homology group to look like? Tell me. Yeah, so you expect one connected component and one class in dimension 1. So roughly we expect, one. So when you look at this birth and death coordinates, this is called the persistence diagram. All the points are essentially above diagonal. It's a simple manifestation of the fact that you die before you die after you are born. Yeah, that's the way of life. And you have nice sample points from the cycle, and we see one the connected component that lives forever, and we see one point quite far away from diagonal, which will correspond to the hole in the center of the cycle. So that will be the beginning of the exercise. And then we'll start to add noise to the point. So we'll start to blur the circle. And we'll see what happens there. All right? Let's go there.
Put all the links for the different files also on the first column. So you just need to have this and or reload the page for the column file, and I put all the links for the different ones in there. So if you use going the column route, you don't need that.
Jan, great to have you here. So let me go again to the Jupyter. So once you installed Goody, if you please stop using Slack for a moment, at least when I'm presenting. What should I do? So once the Goody is installed, we're good. So what happens over here? We are generating point from a unit circle against standard sine cosine parametrization from 0 to 2 pi. Then, of course, because it is one-dimensional, we can plot it, and we do plot it. And then look, here's the important thing. So I mentioned to you that the Rips complexes can be kind of large. This is why in that first line over here, I'm bounding. Somebody is still using this line. Where is Michal? Stop using this line. We are setting maximal radius to 1.8. You can put it to 2.0. We are setting the maximal dimension to 2. Again, that's a kind of benchmark example. You know what to expect. We're not expecting any console dimension higher than 2, especially because our point cloud is embedded into 2-dimensional space. Okay, fair. So that's reasonable. And then we are constructing a Rips complex. And then there's this intermediate step of going through a Rips complex to a simplex to ignore it. And then we are computing persistent homology. And we are getting persistence diagram, which looks exactly as we expect. Non-trivial homology class in dimension 0. A one-dimensional cycle in blue that is born quite early and dies quite late. And a little bit of noise. And it's really because once you look at the point cloud, the points are roughly uniformly sampled, but they get connected for epsilon equals to the distance between the points. Right? So it doesn't happen immediately. The more points you sample, the less you will see of that interval. But in signal processing, there's this signal to noise ratio. This is noise. That is our signal. They're quite well separated. Okay, do it. And then once you do it, you can start adding noise to your point cloud. And do the same. Later on, down in this notebook, you will be able to compute distances between persistent homology of the cycle without the noise and the one with the noise. And the trick is that there is quite a big theorem, which is called the stability theorem for persistent homology, which tells you that if I perturb my point cloud by a level epsilon, then my persistence diagrams in appropriate metric will be perturbed by at most epsilon. The stability of persistent homology. So we can actually check it experimentally over here. So we do a perturbation by epsilon. We compute the right metric. And we compute the distance between persistent homology before the perturbation, after the perturbation. Distance will be lower than epsilon. It's not save the example because we just killed one of the major theorems. All right. So I'll be walking around making sure that everybody's okay, Matthias.
Oh, the link is on.
Shame on you. You can put a QR code on, Let's see. Okay? Okay? Okay?
And then you let me know what will be different, but let's check that first. No, let's see. But it worked. Then you need to run that and then
Good? Good?
Well, I would say the result is the persistence diagram.
So that thing is always bounded by the amount of max. So you are giving smaller noise, the difference will be small. It's always, greater or equal to 0 than bounded by the top by the
Take all the other.
Okay, sorry? We are messing around.
Yeah, I'm messing around.
Good. That's what you're supposed to do. How are you?
Maybe I have a question. Do these functions from this package, do they need simplicial complexes, or is there also some version for like regular CW complexes or something?
Ask me later.
Okay, I will.
Sam, okay, anybody needs help? Can we move forward? Go west. Help. Yes. Go west. Yeah.
I don't think it's maximum radius, but maximum dimension. Then it will work completely because it will add all these final simplices.
The moment you are
We will do questions.
Znaczy zmiana to rozszacowania wymiarów. To naprawdę maksymalny to jest po prostu okazji danego punktu. Chociażby pomysł o tym, że będziesz lokalnych sąsiadów, robisz pismo i patrzysz, które na tym uwagi. Mówisz, że to właśnie się stało. No i to odcięcie, to jest ten wymiar lokalny. Zaraz to trzeba zrobić wszystko, mniej więcej tak naprawdę ma globalny wymiar. Możesz to napisać. Biorę powiedzmy jego kasę osiągniętą. Robię rekord. No i potem robię pisanie. Patrzę, jaki jest wyniesienie na biegu. No i to mi zdaje wymiar lokacji. Ile się bo też miał
Put in two only, then we only have like triangles, and otherwise for each set of n+1 points, then at some point if the distance gets high enough, that's all these.
Okay, anybody needs any more help? Yeah, we are not finishing.
It's good using Rips, Rips is the most visual and calculated. I'm trying to see from which they mentioned it, but where crashing like the crashing with them, it's like mature. Well,
Yeah, you just run out of run because
Oh, somebody's computer was like,
oh, I should find 5 minutes. It's like 5
so the thing that would be nice thing you can just after syntax you can try to bring the numbers.
Oh, right, okay.
Yes. That's the number of syntaxes.
okay, anybody else need help?
Sorry, I have a question.
Sure.
Can I answer it? Give us the minimum number of symbols for triangulation.
Nobody said. He doesn't understand the problem. Cheyenne, you know the problem, if I give you a manifold and you tell me the minimal number of simplices in the triangulation, that's
In general, it's undecidable. I think it's a result of Schmoll-Weinberger.
Yeah.
But for real things, it's doable. Like, in 3D.
yeah. Okay, yeah, 3D is
Yeah.
Okay.
I mean,
You get weird objects, bouquet of spheres, and it becomes undecidable.
yes. For 3D is, but again, for typical engineering applications that there are minimal triangulation and having the reasonable triangulation of acceptable aspect ratio of simplices, that typically you are not chasing for minimality, because chasing for minimality is much more expensive than running those algorithms. You can also simplify your triangulations using, for instance, discrete Morse theory, and well, Nick Scoville will be speaking about it. you are. But you should talk to Nick. You are coming to Benjamin, right?
Yeah.
Good. Very good, very good. Okay, and everybody happy with this example? Let's see how bad we are doing with time. Terrible. Anyhow, so we can use it, this machinery for different things. So one thing we are doing over there. So looking at the bone quality, osteoporosis detection, etc., etc. I won't say much more. And material science. Again, I don't have too much time to speak about the details, but it allows us to screen hypothetical materials just to select those which potentially may be useful, and only then doing, for instance, quantum Monte Carlo simulations to actually find out if they're good or not. We can do a time series analysis. If you want to see a streaming of a talk by Michał on a conference, there will be a streaming of the talk by that guy over there who's not listening. And, there are multiple resources, so I think we'll just put the slides online and you can click in one of those links. But it will get you to much further introduction to persistent homology. Yes.
How this transition analysis different from the one that is used with the again from time series to point cloud.
It's based on the takens of any PR, yes. Well, once you do take a takens of any, so let's see. Let's actually speak about the things. Those things are used. There is work by Jose Pereira, John Harver, and that crowd. And if you Google for ciphers, they were looking for detection of some periodic behavior, and that work started with Vinda Silva, NVJ, and the others, and back like more than 10 years ago, they were trying to detect a periodic notion. What they were doing is taking the many theorem and then detect periodicity using one-dimensional. That's more or less one of the possibilities, but what Michał will be talking about is not this. This is not. Again, we are building up on taking the many theorem, but in different ways. Okay. If you want to know more, something else. Okay. And some books. Again, we'll put the slides online, so you don't need to take a notes right now. It will be provided later on. Of course, we don't have time, so we won't play with percolation. Unless we want to play with percolation, then there is an appropriate notebook which you can find anyhow. Okay. So what persistence is doing? We are having a point cloud, and then we are getting a gadget. This is this persistence diagram. You can see it and say, okay, that looks like a one-dimensional circle. Fair. We can compute distances. We can compare it. We can look, okay, is this noise look similar to that noise? Coming back to your question. But somehow, and again, let's go back to the motivation from Datasaurus and Scobet's chapter. Sometimes we want to visualize it. You want to have something visual. For instance, if you look at those two data sets, from a perspective of persistent homology, they will be very similar. One cycle, roughly one connected component. Sometimes those things, which we call flares, are important. How can we detect flares? Let's see how much time I have. So let me start with something easier. And then if we have time, we'll move to something more difficult. So let me start with a ball mapper. And again, instead of giving a definition, I want to tell you, if we have this point cloud, perhaps embedded to 100-dimensional space, how can we visualize it so that we capture a simple fact that it has a shape of a letter Y? So what we are doing is we are starting from this epsilon net. What's an epsilon net? First, I'm selecting my favorite positive number, epsilon, and I'm creating a subset of this point cloud, and those are those colored points over here. And the subset need to have a certain property. And the property is that every point from my point cloud has a point from my epsilon net, has a color point not farther away than epsilon. Right? So if I pick any black point, say this guy, and I'm looking epsilon around, I will find at least one point from my epsilon. That's a definition. I can find it, but the definition also means that if I place a ball of a radius epsilon at every point from my epsilon net, I will cover my whole point cloud. So my whole point cloud will be contained in the union of those balls. And now what I do, if you are an algebraic topologist, I will just say I'm taking the one-dimensional nerve of that cover. If you are not, I will say that, okay, I'm building an abstract graph. I have it here. I'm taking an abstract graph whose vertices corresponds to elements of my epsilon net. So I have as many vertices as I have the colored points. And I put an edge between two vertices if the corresponding balls are covering at the same time a point. So for instance, if I take, that point from my epsilon net and this point from my epsilon net, the corresponding balls are covering certain points, and therefore I will have an edge between them. Those two balls don't intersect, so I won't. But at the end of the day, I'm getting a graph like this. It roughly has the shape of the letter Y. And there's one more thing. So imagine that I have a function defined on the top of every point. We'll be playing with Boston property dataset in a second. In Boston property dataset, what we want to infer, so you have essentially 13 or 14 characteristics of a property in Boston areas, and you want to infer what's the price of the property. It's real estate type question. So once we will cover those regions, every ball contains certain number of properties, and then I can aggregate those prices within a ball by, for instance, computing an average. So I get an average price of a property per ball. And that gives us a coloration function. I'm sorry for jumping for the slides. I think the most famous example of the coloration we have in this. That's a work by Monica, and I forget the first name, Levin and Gunnar Carson, and they work on the breast cancer example. Long story short, there's a control group, that's a breast cancer population, colored by the number of months the patient survived. The farther away you are, the worse it is. But they found, that region with a perfect survival, which was not known before, with certain genetic properties. So that's an example of a correlation function, survivor, for instance. In our case, we won't play with that serious things, we're just playing prices, right? Now, wait a second, where are we? Long story short, yeah, here we are. Does the algorithm make sense to you? Or you try to use it? Thank you for answering. I would appreciate a little bit more enthusiasm about this. Yeah. Hey. Okay, so you go back. Ouch, ouch, ouch. Either you use Jan's link if Jan has fixed it already, or you go here and you go to exercises in Ball Mapper, which is a Python version, unless you want to use R. Speak up.
It's outdated. Without it, can keep install it and go on.
Okay, we'll get there. So let's download it and then we'll do pip install, right? Yeah, I know.
No, either you use that works. But we have better version.
Yes, so tell us how to do the better version.
You just go to my GitHub.
Okay, Davide? There is a better version just to support pip install.
Yes.
And Davide will. So I think if you put Davide Gunari GitHub on Google, you'll find a picture of a guy with a bike. That should be the right place to go to start looking.
Yes. And there is a nice code that.
Sorry, I didn't have time to update it. I didn't mean to offend you.
No. It just, that if they want to expand it, so let me just. So I'm updating so it works with color. Okay.
Okay, so what do you do?
So you go to my GitHub.
You put
This one over here. Or you just search for Pawel mapper. So this is this GitHub over here. Just you Google Pawel map. And then the nice thing, if you want to open that on Google Colab, so once you have it here on this GitHub, you just replace you add to GitHub, you add to Colab.
Yeah, so you
So
replace
this
GitHub to call up URL.
So this is a nice trick to open whatever GitHub repo that you want. You just add GitHub to Colab, and then that's my thing. Yeah. How do I?
Yeah, I'm not sure how to zoom that here.
No. Well, yes. Well, this is my GitHub, and then you just in the URL in GitHub you just add to Colab.
Oh, I see.
Yes.
So once more, you go to the GitHub, and then you go to the URL bar. When it says GitHub, you remove GitHub and you
No,
type.
you add Colab to Colab.
When it says GitHub, you add after GitHub to Colab, and you hit enter. And once you hit enter,
so over here, it loaded up my repo, and you can open whatever notebook you want. So you want the Boston property, right?
yeah, I want the Boston property. This.
Yes.
One word.
And as usual, you need to pip install Pawel. Oh yeah, that is me.
So you won't getting an error?
Well, because
File not found. Oh, just remove it.
now I update it so you can pull it from my. Yes, now it just. It was a last minute.
Yeah, that's it. Now go to GitHub.
One question. I'm still getting.
You say just to change.
Oh, so sorry.
You say just to change GitHub to
Two
column.
column. Yes,
So
you had two column over there. Oh, sorry. Yeah, sorry. I updated the second cell and not the first one. Two column. No. It's just you keep GitHub, and at the end of GitHub you had two column.
two column.
Yes.
You know, you have to create one
So-
say.
Without any space, two
Yeah.
columns.
Just. But just give me a sec, so I can.
Okay. It works. Thank you.
But probably you need to reload it in 1 sec, because it will probably get you an error.
GitHub to collab,
GitHub to collab, yes.
but this is two or the digit two?
No, it's two, TO.
This is collab with double L?
Collab now is singular.
Single.
Okay. Okay, now it.
Try again. Yes. So,
You load the file to
Or otherwise.
What should I do?
Well, just try to reload it as soon as. As soon as we go to service. Just this garage makes more sense. Yeah. Yes.
So with the file in the bottom.
So the file will take some data, but now it should be.
So it would be the same.
But now I should upload the.
They have a good.
I'm having problems.
And then, yes, and then you need to keep control the. We just add a cell on top. And we just. One of those. Yeah, just you need to press escape and then D. Yeah, with the exclamation mark. You can install all the Bible. We have some deep space installed with the Bible.
We need to do some data.
It should be working now. Okay. And if you're having problem with the data, just reload the data. Just reload it.
Is there the BNF?
So if you're, of course, if you're running this on Colab, you need to pip install ball mapper before importing that. So over here, you just add, as we did before with Rudy. Install.
Question.
Yes.
I'm having problems here at the BNF.
Or you still need to run that.
Oh, I forgot. Yeah, I did.
Okay, so now you import, you need to also run that.
Any questions?
variable price in the
Okay, I'm fixing.
yeah, so basically this is a big
And then
yeah, so basically you just go back to the original equation, you do the same thing. Yeah, yeah, yeah. So basically, okay. So
Okay, guys.
the closure of the don't have to do it anymore. Just
Some error here.
so go back to the original page, so back to matter.
Just, you know,
And we just yeah, yeah. I think that the input update the thing you need to do the so keep the code there. So if you do the Bible map and then looks everything. Yeah, there's that. Then just do again, just cut the lab and then you can so you put the lab. Okay. And then the
Yes.
Have you uploaded the data with the right column names? Because there seems to be a problem with the price name.
Yeah, I'm over.
No, because we already got the.
Okay.
No, okay. Find it.
Try a different example.
No, okay, it's instead of price, it's V30.
Yeah, so when it's reading, the columns have different names.
Yeah.
I think.
Yeah.
So what was the name?
It's the last one, so V13.
V13. We change price to V13.
Okay, so everything is working now.
All right.
Yes, okay.
Yeah. Yeah, okay. You have a lot of time. We're good?
Yeah, you can go to this.
But if you reload,
Yeah, we're not sure. Yeah, the change price to V14. We uploaded the wrong file with the wrong column name.
well, it's the last one. But, yeah.
How do you manage? Pretty good. How about you? Good? You good? How about you? John? John?
Yes.
Why it doesn't work? Because this works.
Okay, that works. Then you need to install the. Now, let me add here the cell. So if you need to add this thing. If install.
Okay.
Yes. So comment this if you are on all of.
Did you get
Yeah.
the add coloring door? One.
Hey, David, so this is V14.
V13.
This is
Yes.
V14 for you.
What is
if you know that you cannot-
Yeah, no, I now adding the thing. So now it should be one. Okay. So if you wait 30 seconds and then reload it. Sure.
Okay. Just that was a V13. Maybe you need to.
Yes.
Okay, so now
This changed the data was in
so this is now the cool thing with Dlotko is every time that I push a change, automatically refresh it. They just need to reload it.
Yes, let's see.
But
So we roughly have 20 minutes.
but you know also
And I should actually show the whole thing. Okay, everybody has the Bowmaster examples for the simple concentric cycles and the Boston property working. That's work for you. That's work for you. Good? You're good? Sharon, you're good? Good? Okay. So let's see. We have 15 minutes, and I want to show you. So Bowmaster is a pretty new thing. We are kind of still trying to promote it, but this is not how it started. It started, let's say, in the 40s by a monsieur called Red. Not Red, Red. So he was French. How you read it? Yes. That name. This one's Red. It's what? It's Red, of course. And let's see, do we have an English speaker? Try, I mean, okay, you know how to read. We have an English speaker who don't know how to read it. So, yeah, how you read it? Read. But the name, the guy was French, so you read it, Matthias? Red. So that's how you should say it once you have a French person on board. Matthias, you can say read, but that's right. Okay. So here's an idea. You have a manifold M, and you have a function, making every point from this manifold a real number. And what I want to do is I want to use those two pieces of input to define an equivalence relation. How I define an equivalence relation? Well, I will say that 2 points are equivalent if 2 conditions are satisfied. First of all, they need to have the same value of the function f. F of x equals 1, right? Okay, fair enough. But there is this additional condition, then x and y need to belong to the same connected component of the fiber. Let's take a look at the example. So in my function, and you know, whenever you're doing Morse theory or the red graph, the first example always, you know, a standing torus with a function being this coordinate. That's always by definition. If you are on the lecture when there is no the first example, just get out of the lecture because it's not the proper one. Okay? So, what are the fibers? So if I have a value somewhere here, what will be the inverse image of the fiber? Well, it will be all the points on the surface of the torus that are all resulting. So it will be at the form circle, right? So if I take all the points having value somewhere here, the inverse image will be a single circle. So essentially, if I take 2 points having the same value, they will be in the same class because there is only one connected components in an inverse image. It is not the case for points over here, because once I take an inverse image, I get one circle over here, another circle over there. So there is this additional condition that we check. There will be 2 classes of abstraction over here. Symmetrically, the picture is symmetric, only one class. And once we actually compute the quotient, oops, here it is, with the quotient topology, under some mild assumption, namely f is a Morse function. You know what it is, that's fine. You don't know, it's also fine. And the quotient space will be a graph, will be one-dimensional CW complex. And that's the red graph. That's the finish. So the original mapper that I'm gonna Carson, Facundo Memori, and Gorget City, it's an attempt to take this construction in the following setup. So we know our function, as we used to know it in case of manifold, but we don't know our manifold. We just know a collection of points sampled from this, perhaps with a little amount of noise, not too much. Okay. And now question is, can we do something similar? Can we mimic the original construction of the rep graph in case when you have a discrete point cloud instead of a manifold? So let's try to do it. So this time we have a finite collection of points sampled from a manifold and the function f. Slang alert, f will be called a lens function. So when I speak lens function, I mean a function from my collection of points into real numbers. And now I want to define a relation. This time it will not be an equivalence relation, a relation. I will say that 2 points are in this relation if, okay, now we are speaking about finite amount of data. Requiring that f of x equals f of y, I mean, that happens with probability 0 in general. So if we have 2 points, more points for which a generic function has the same value, that's strange. Let's put it like this. So we shouldn't require f of x equals f of y because that will never happen. We should require that they are close to each other. What does it mean? Wait for the next slide. And then the second requirement over here is that they belong to the same connected component. This time we don't have connected components because we only have discrete collection of points. What's the nearest analog of, you don't say it. What's the nearest analog of connected components from a continuous topology in case of data? Bastards, very good. So, okay, I'll tell you a joke, but we don't have time. Okay, what does it mean that f of x is close to f of y? So in practice, what we do is we are taking our point cloud and we are taking the range of the value of our function. We are covering this range with a collection of overlapping intervals. This one. So we have black intervals, red intervals, we are covering it. There are 2 parameters we are typically choosing. Number of intervals that cover the range and the percentage over overlap. How much from 0 to 50% do 2 neighboring intervals overlap? Okay, and then f of x will be close to f of y if they are mapped to the same interval. That's our measure of closeness. Okay, it's not ideal. We can argue that perhaps we can do better, and perhaps we can. And that's how we do in the standard way. And then, if they end up in the same interval, so if f of x and f of y are in the same interval, then we are taking inverse image of the interval, and it contains certain amount of points, and we are running a clustering algorithm there. It will give us a number of clusters, and we check if those 2 points are or are not in the same cluster. That's the analogy. So let's see. If I take this interval over here, Well, I would say that a reasonable clustering algorithm will tell me that there's one cluster. So very much like in the previous case, there will be only one class. But if I take, let's see, this interval, I'll get a bunch of points over here and a bunch of points over there. I would expect that a reasonable algorithm will tell me that there are two classes. So, you know, the points over here will be in relation because they have F value in that particular interval. And they belong to one cluster. And you know, the points from this cluster also have their value in this interval, but they are forming another class. Right? And then every cluster will correspond to a vertex. Two clusters, if they intersect, they will intersect because our intervals intersect. Right? So there is a room for intersection between different clusters, even if we are not using soft clustering. If they intersect, we put an edge. We get a graph, we call it a mapper graph. That's all it is. So think about that. That is a formalization. So let's go formally through this once we have some intuition. So if we start with a finite collection of points sampled from a manifold, and we have the length function F. And we cover the range of F with overlapping boxes. And then we fix the clustering algorithm. And well, we define this equivalence relation. That gives us collection of overlapping clusters. Every cluster corresponds to a vertex. Two intersecting cluster corresponds to an edge. And that's a mapper graph. Does make sense? Okay. So let's see. Do we still have time? 5 minutes, although we should be wrapping up quite soon. So there are analogous exercises, as we did for ball mapper, that you can do for a what I call a conventional mapper. The additional thing you need over here is this length function. It's not easy typically to find it, and you know, we have some experts trying to optimize it. You can raise your hand. If you want to hear more, talk to this guy. You can also talk to me. You won't answer. And well, you know, it's along with persistent homology, it's one of the working horses of TDA. Because again, if we go back to our motivating examples from statistics, it allows to visualize point clouds. So we can see if they look similar or they do not look similar. And well, it's helpful when you're analyzing data. But because I'm the only person between you and lunch, I think I'll stop over here, and I'm happy to continue discuss kind of one-to-one later on. Thank you for your time, and if you have any questions, ask them. Okay, so let's stop here. And I think I'll stop Zoom.
Maybe a quick announcement. We sent an email around with a link to join a Slack channel. So just in case we need to share other links, or just if everybody joins, then you can also communicate with